Hello, welcome to this video 6-1 part B. In this video we are going to hammer out examples of left, right, midpoint Riemann sums and then do a little bit of interpretation in context. So without further ado, we're going to go ahead and jump right into example number 5. Remember, our learning intention is that we will be able to approximate definite integrals using Riemann sums. So example number 5 says approximate the integral from 0 to 10 of f of x dx by using 5 rectangles of equal width, n equals 5, and a left Riemann sum. Draw the rectangles on the figure. Alright, so we want to go ahead and we want to use 5 rectangles. So if I have 5 rectangles, what this means is that my width, I'm going to have to go ahead and take my width, I'm just going to say width, which is from 0 to 10, right? So 10 minus 0, and I'm going to divide that by 5. So each width is going to be 2. So I'm going to go ahead and just draw those rectangles on here. The visual really helps. I'm going to have 5 rectangles with widths of 2. Okay. And let's do purple, and then orange. Do orange. There we go. Okay, so those are my widths. And then for the height is going to be equal to, now this is a left Riemann sum, so I'm always going to use the left. So that's going to be f of 0. It's going to be f of 2, right? It's always that left point of my interval. F of 4 and f of 6, f of 6, and f of 8. F of 8, okay? All right, so let's go ahead, and again, all of that is kind of the idea that should go into prepping for the Riemann sum. So 0 to 2, there's the height of my first one. We have 2, the height at 2 is right here. So here's my second rectangle. Okay, and third rectangle is going to be at f of 4, which is also right about here. Okay, f of 6, right here. Right, and f of 10, sorry, f of 8, which is also about here. Okay, so there's the rectangles. All right, so I want to go ahead and approximate the integral from 0 to 10. Again, this is the area, the integral of, or from 0 to 10 of f of x dx, which is approximately, because remember, a Riemann sum is approximately, not exact. All right, so I have my height, f of 0 is 0, okay, times the width, which is 2, plus I'm going to have the height of f of 2, which it looks like it's 4. Now you can visually approximate if it's clear, but they also give us a table. Now most Riemann sums will see exact AP FRQs are given in the next following page. They're usually in table form. So f of 2, if I go down here to 2, the height of the function is 4. So I can say, okay, 4 times 2 plus the height of f of 4, which is also 4, times 2, right? And it's the area of the rectangle is just height times width. So then I have plus f of 6, which is 2, times 2, plus f of, was that 8, which is 2, also times 2. Okay, so I can go ahead and calculate this. This is 0 plus 8 plus 8 plus 4 plus 4. So that looks like 24. That is the approximate area of the left Riemann sum. Okay, example number 2. Here we're asked to approximate the integral from 0 to 6 of the square root of x squared plus 10 dx using a midpoint Riemann sum with 3 equal subdivisions. Now again, if I have 3 equal subdivisions, okay, and my width is 6, so 6 minus 0, I'm just going to write here, width is equal to 6 minus 0 divided by 3 subintervals. My width is going to be 2. So my first rectangle will be from here, 0 to 2, the second from 2 to 4, and the third from 4 to 6. Now, it's a midpoint Riemann sum, so I'm going to be using the middle value. Okay, so for my first interval, that's at 1. I want the height of the function at 1. There's my first rectangle. The height of my second rectangle comes from the middle point, which is at 3. So the height of the function at 3, okay, plus the height of the function from the middle point, which is at 5, okay, and there you have it. All right, so let's go ahead and let's calculate this. So we have the integral from 0 to 6 of the square root of x squared plus 10 dx is approximately, so I want the height of my first function, which I'm plugging in 1, so f of 1, or the square root of 1 squared plus 10, okay, times 2, plus, now I'm going to plug in the height at 3, so the square root of 3 squared plus 10 times 2, plus the square root of 5 squared plus 10 times 2. Now this is numerical. You could go ahead and stop here. Again, on the AP test on the FRQ, that's your answer. Now, if you did have to go ahead and do some simplification, we could go ahead and work with this. This is obviously 2 times the square root of 11. 1 squared plus 10 is 11, so 2 root 11. Plus, here we have 2 root, what is that, 19? Let me make that in blue for you. So 2 square root of 19. Plus, it looks like 2 times the square root of 35. And you might further see that reduced if they factored out a 2. So root 11 plus root 19 plus root 35. And I can't combine any of those square roots. So there you go. That would be an exact value. And without a calculator, you couldn't take that any further. Okay. Example number 7. Example number 7 asks us to approximate the integral from -10 to 5 of 2 to the power of x minus 8 dx by using 5 right-hand rectangles whose widths are determined by the intervals separating the following x values. So a lot of times Riemann sums will give you intervals, or a table of data will just give you the intervals, and they say use these intervals. So they want 5 rectangles being separated from -10 to 4. So from -10 right here all the way to -4. -10 all the way to -4. There's my first rectangle, okay? Now, it's important to note that width right there, right, from -10 to -4, that's 6. That width is 6. My second rectangle goes from -4 to 0. So -4 to 0. The next one goes from 0 to 2. The third one goes from 2 to 3. It's just a 1. And then lastly from 3 to 5. 3 to 5, all the way here. Okay, so there's the widths. Now, and obviously I can add in the widths here. So we have 4 and then 2. Okay, our height, again, this is a right-hand Riemann sum, right. So I'm going to use the right value. Okay, so the height of the rectangle is going to be determined by -4. So there's my first rectangle here. Okay, note, it is below the x-axis, so that is a negative quantity. That should have a negative value. Now, the second one, a right value is determined at 0. So here is the height of my second rectangle. The third one's going to be determined at 2. So here's that one. The fourth one determined at, what is that, 3. Okay, and that's, looks like it's 0. And then the last one determined at 5. Determined at 5. Okay, so we want to determine or calculate what that value is. So let's go ahead and do some computations. The integral from -10 to 5 of 2 to the power of x minus 8 dx is approximately, so my first integral, that is going to be 2 to the power of -4 minus 8, okay, multiplied times 6, times the width, which is 6, okay, plus, now I have the height is going to be 2 to the power of -4 minus 8 times the width of 4 plus we have 2 to the power of 2 minus 8. That's width is 2. And then we have plus 2 to the power of 3 minus 8, and that width is 1. Plus, lastly, we have 2 to the power of 5 minus 8 times 2. Okay, and there is our answer. Ta-da! Not too bad. Not too bad. Okay. All right, so those were some examples that incorporate graphical design. You may see these on multiple choice questions. Here are some examples pulled directly from a free response question in the AP exam. We're given a table of data and some context. They say a large department store opens at 9 a.m. and closes at 9 p.m. The rate that people enter the store in people per hour, so it's important that they say the rate that people enter the store in people per hour is modeled by the function p prime of t, where t is the number of hours since 9 a.m. The table above contains values of p prime of t at selected times of t. Use the data in the table to answer the following. Okay, so I have a table of data. Notice they say t equals 0. This is 9 a.m. That's important to just kind of think about. And when t is equal to 12 hours later, the department store closes at 12 p.m. Okay, so example number 8. They say use a left Riemann sum with 3 subintervals to approximate the area between p prime of t and the t-axis from t equals 0 to t equals 5. Indicate units of measure, and then they say what does the value represent in the context of the problem. Okay, so let's go ahead and calculate this. All right, we have 3 subintervals. So our width, if we're going from 0 to 5, notice here in the table, so 0 to 5, and I want 3 subintervals. These are values indicated in the table. So I'm going to have my first rectangle be from 0 to 2. Here's my first one. Okay, and then I'm going to go from 2 to 4. Okay, and then I'm going to say 4 to 5. So notice it matches how many rectangles from this point to this point, this point to this point. That matches the how many subintervals that they want. Okay, so our width changes. Width changes in these examples. Width changes. All right, so I'm going to say here, I'm going to generate an integral. So I'm going to say the integral from 0 to 5 of p prime of t dt with respect to t is approximately. So this is a left Riemann sum. Okay, so I have p prime of 0, so that's my height, p prime of 0, and the width is 2, plus p prime of 2 times, looks like 2 also, the distance here from 2 to 4 is 2. Sorry, this one was also 2. And then lastly, the width from 4 to 5 is 1. So I'm going to add the height, p prime of 4, times the width, which is 1. Okay, so this is going to be equal to, so p prime of 0, that was 11, so 11 times 2, plus p prime of 2, that was 30 times 2, plus p prime of 4 was 54 times 1. So this gives us 22 plus 60 plus 54, and that's going to be equal to, looks like 82, 86, 136. Okay, and this is people, because we're multiplying people per hour, right? People per hour. This is people per hour, and then this is in hours. People per hour, and then this is in hours. So when we multiply those, these cancel, and we get people, right? Okay, so what does this mean in context? This is the amount of people per hour that are entering, and we're multiplying times hours, so 136 people. Remember, integrals are accumulators. I'm taking up and I'm accumulating how many total people that we have here. So this is the amount of people entering the store. That's what p prime of t means. So we can say from 9 a.m. to 5 hours later, that's going to be what, 2 p.m. 2 p.m. 136 people. I'm going to say 136 people total enter the store. And maybe I'll even throw in the word about here, because it's approximate. So from 9 a.m., 5 hours later, I don't know why I'm so uncomfortable. 3 hours would be noon, 2 hours, yeah, to 2 p.m. Total 136 total people enter the store. So that's what it means in context. Okay. Example number 9. Use a right Riemann sum with 4 subintervals to approximate the area between p prime of t and the t-axis from t equals 4 to t equals 12. Using correct units, interpret your answer in the context of the problem. I'm going to have you pause the video. I want you to try this example. I'll go ahead and show you the example or the solutions here in a moment. All right, here is the solution to example 9. The integral from 4 to 12 of p prime of t dt is approximately, using a right-hand Riemann sum, 179 people. Now, the widths, looking up here, they wanted 4 subintervals. So I have gone ahead and drawn these subintervals. So here's our first interval, starting from 4 to 5, 5 to 6. Those widths are 1, and then 6 to 9 is 3, and 9 to 12 is 3. So those are the widths. The heights are determined by the right side, the right point. So we used p prime of 5, which was 26, p prime of 6, which was 21, p prime of 9, which is 44, and p prime of 12, which is 0. So you can see those calculations here. And we got 26 times 1 plus 21 times 1, that gives us 47, plus 44 times 3, 132, plus the 47 gave us 179, and our last one was 0. 0 times 3 gave us 0. So the answer is 179 people. Now, what does that mean in context of the problem? In context of the problem, well, we can say from t equals 4 to t equals 12. And then again, another way of saying this would be from 1 p.m. to t equals 12, which would be 9 p.m. About 179 people total enter the department store. Okay? And that's what it means in context. All right, example number 10. Example number 10. This is one that we've done one example before. We want to approximate the value of the integral from 0 to 12 p prime of t dt using a midpoint Riemann sum with 3 subintervals as indicated in the table above. Using the correct units, interpret your answers in the context of the problem. Okay, so the first thing that they throw at us is they want a midpoint Riemann sum. So we're going to have to take the midpoint, and then they say 3 subintervals. 3 subintervals from 0 to 12 as indicated in the table above. So I'm here, and I want 3 subintervals from 0 to 12. Okay, so if I want 3, 0 to 4, that's going to be 1. 4 to 6, that's going to be 1. And then 6 to 12, that gives me my third one. Okay, so this is kind of a unique example, not common. But it's the data indicated by the table. Notice if it was not indicated by the table, 0 to 12, it was equal subintervals. I would divide 0 to 12, so 12, by 3, which would be a width of 4. So 0 to 4, I have that interval, but notice, do I have 4 to 8? I don't have data on 8. So they want it indicated by the table, so here is our widths. So just making note, our first width is 4, our second width is 2, and our last width is 6. Okay, so there's our widths. And then also they want midpoint. Midpoint. So what's the data, or where's our heights going to come from? Well, the midpoint of our first rectangle is 30. The midpoint of our second interval is 26. And the interval, or the midpoint of our third interval is 44. So there's our heights. Okay, let's go ahead and approximate this and try this example out. Okay, so the integral from 0 to 12 of p prime of t dt is approximately Our first width was 4, and our height was 30. So 30 times 4 plus, I think the width was 2, but our height was 26. So 26 times 2 plus 44 times 6. Okay, and this is going to be equal to, and you can just trust me on this one, 436 people. Because again, our rate, this is people per hour, and this is times hours. So 436 people. What does that mean in the context of the problem? Well, from 9 a.m. to 9 p.m., about 436 people total. I'm going to use that word total. Total people entered the department store. There you have it. All right, that's going to do it for this video. In this video, we went ahead and went over our learning intention, which was how to approximate definite integrals using Riemann sums. We covered a left Riemann sum, a right Riemann sum, and midpoint Riemann sum. Go ahead, like and subscribe this video. Next video, we're going to talk about the trapezoidal rule and how we use that to approximate the definite integral. Catch you next one. See ya.